All right, AP Environmental Science. This is a continuation of topics 3.4 and 3.5. The other day we started talking about population characteristics, and in this lesson we're going to take that a little bit of a step further and talk a little bit about how populations grow and some of the conditions in which populations need to grow in certain ways. So we're going to start off today with just sort of a definition of growth rate or population growth rate. It says here that we can define growth rate as the number of offspring an individual can produce in a given time period minus the deaths of the individual or its offspring during that same time period. So, I mean, you can probably read that a couple times and like it may not make a lot of sense to you, but the growth rate is basically a number. And here's kind of what you need to understand about it is if the growth rate has a positive value to it, then the population's going up. It's growing, right? You know, the higher the rate, the more it's going to grow. And if the growth rate is a negative value, that means the population is declining. If the population growth rate is zero, then the population's not growing at all. All right, so that's kind of, I think, an important thing just to remember about growth rates. All right, now there's a term here called the intrinsic growth rate. And for this term, there's a variable that goes along with it, which means we're going to use this in some math problems here in a couple of minutes. But intrinsic growth rate is also known as the biotic potential. And basically what this is sometimes populations are going to grow under ideal conditions. So for example, let's say a population of rabbits or something, you know, let's say they have all the resources that they need, you know, all the food, all the water, all the living space, there's no predators, then they're going to grow intrinsically. You know, there's nothing like there's no limiting factors that are keeping them in check. So you can probably imagine that if a population does grow this way, you know, then the births or the birth rate will far outnumber the deaths in that population. That's all because there's nothing really keeping the population in check. Now, when would populations actually grow like this? You know, when would you get a population that kind of grows intrinsically? Well, good examples of this are what we call invasive species. You know, invasive species are basically some organism or some species that normally doesn't live in an area. And it's usually like a non-native species. That means it's not like native to that particular habitat. And for whatever reason, it's been introduced into that habitat, and it doesn't have anything that kind of limits it. You know, there may not be any predators, or there may be plenty of food for it. So it ends up growing intrinsically. A really good example of this is something called a zebra mussel. Zebra mussels are native to Asia, different parts of Asia. They normally don't live in the United States, but they were actually brought over to the United States back in the 1980s, mainly by the shipping industry. You know, they would be stuck or like attached onto big boats, and these boats would kind of make their way into the Great Lakes regions, the U.S., mainly through the Hudson River, and they would dock and they would dump off whatever you materials they were bringing over to the United States, whatever was being imported. But you know, some of these zebra mussels would fall off the boats and they would get into the lake. So these little red dots, what they're showing us are populations of zebra mussels that we found back in 1989. These were not a species that was native to our country. So these little red dots are just those populations. So I mean, you look at it and you're like, okay, big deal. There's a couple little populations here in Lake Michigan, you know, a couple up here in Lake Superior. You got a whole bunch of them here in Lake Erie. That was kind of the big source of the problem. But take a look at what we see today. You know, these are zebra mussel populations, not just in the Great Lakes, which they're extremely common, but they pretty much have made their way into just about every single waterway, mainly rivers and lakes, all around the country. Right in here, it's kind of hard to see it, but this is the Mississippi River. And notice the accumulation of them down here in Louisiana. See a whole bunch of zebra mussels in the Mississippi, plus all the Great Lakes. You even see them out west, like in the San Francisco Bay. They've been found there. So these populations have really multiplied. Now, the big reason why they've been so successful is where they're normally from, these different parts of Asia. There are predators that kind of keep their populations in check. But in the US, those predators are not here. So essentially, there's nothing keeping the zebra mussel population from overpopulating, and they're just taking over waterways and clogging up, pipes, and I mean, they're just becoming a nuisance. Plus, they're really messing up the food chains. They're feeding on a lot of the organisms that normally other fish and other organisms in the Great Lakes would feed on. So, not only are they overpopulating, but they're having a big effect on food webs and food chains, especially in the Great Lakes and other rivers and streams around the country. So, big problem with those invasive species. Here's another example of one. This is called the kudzu vine. Kudzu vines are not native to the United States. This is a vine that normally lives in Japan. This picture here, what you're seeing, this is a picture that was taken in the state of Georgia. I actually found this on the internet a couple weeks ago, and these big like things that are sticking out of the ground, these larger things, these are actually trees that are just covered with these kudzu vines. Now they were brought over to the United States from Japan back in the 1800s. They were mainly brought over as like a decoration, like an ornament. They would like hang them on their porches, and people thought that they looked nice. But what they found was that in the United States, where the weather conditions, the climate conditions, are actually much different compared to Japan. It's allowing these vines to grow uncontrollably. For example, in Japan, it freezes. They actually have winters there. In the southern part of the United States, like down in Florida and Georgia and the Carolinas, it doesn't really freeze there very often. So these kudzu vines are just exploding in population because, again, they don't have that limiting factor keeping them in check. This is actually an extremely expensive invasive species to control. It says here, right in the middle of this slide, it mentions that there's an economic impact, right? $100 million to $500 million are lost per year just in forest productivity alone. So these vines are actually inhibiting, the natural productivity of the forest. That's becoming an issue. We've got to pay people to go out and mow and kind of hack down all these vines. There's millions of dollars every year that we spend on repairing damaged power lines because they grow on top of power lines and stuff. So economically, it actually takes a pretty big toll. Now, some things that we've tried to do, to kind of remove it and kind of control it. Mechanically, again, we've tried to cut them down. Chemically, we've tried to produce like herbicides. The problem with that is a lot of these chemicals that we use, when they get into the environment, they actually cause, sometimes more damage than what they're worth. Some of these chemicals can impact other organisms, including humans. We've tried to use biological control, things like goats and sheep to just like eat the kudzu vine. The problem is they don't eat that much, so they're kind of slow at controlling the growth. They've even come to the point where they've tried to find ways that we can maybe produce commercial products. One thing I found on the internet the other day, and I actually have some in my classroom, they actually sell kudzu jelly. It's it's a jelly. It's like edible that's made from the kudzu vine. It's actually pretty good. So if you want to try any, I actually have some in my fridge in the back. But anyway, so I don't know. This is just another example of an invasive species. All right, now when it comes to population growth, I want to kind of talk about two different models today. And these are basically graphical representations that we use to kind of understand how populations are growing. One of them is called the exponential growth model. The other one's called the logistic growth model. You might be familiar with these from math class, so hopefully that's the case. So I'm going to kind of go over each one of them with you individually. Now, the first one, called the exponential growth model. Before we get into the graph of it, there is a math formula that I want you to be somewhat familiar with. I'm going to give you this formula on quizzes and tests, but we're going to have to be able to understand what the variables mean and kind of how to use it. It's actually really easy, but you're going to need for this a scientific calculator. All right, so if you have one, go get it. Pause the video if you have to, and go get yourself your scientific calculator. All right, so this equation, kind of starting from left to right, you'll notice here how we have this variable. It's called n sub t. N sub t is the future population. So let's say you have a population of rabbits or something, or a population of, I don't know, zebra mussels, and you want to know what that population size is going to be, let's say a month from now or 2 years from now or whatever. Okay, so the future population is what we're trying to find using this particular equation. So in order to find the future population, there's a couple of things that we have to know. Number one is we have to know what the current size of the population is. So if you want to know what the future population is going to be, you got to know the current size. So n sub 0 represents the current size of the population. That should be pretty easy to understand. Now, another thing that you have to know, you'll notice the variable r that's in this equation here. R is the intrinsic growth rate. It's just, how fast is the population growing? Is it growing at a rate of 4% or 10%? It's usually a percentage as far as how they'll give that to you. All right, so we have to know that. And again, that'll be given to you. You'll see in the problems that we do here in a second. Another thing that we have to know is time. So you'll notice T up here is in this equation. So T stands for time. We talk about 1 year or 2 years or 3 years. And typically that time value will be a value given in years. Now, another thing that we have to know for this is where some of you may be a little bit confused with the math and some of you may not be. But you'll notice that we have this variable E that's in the equation. E represents something called the base of the natural logarithm. All right, I want everyone to look at their calculator. And on your calculator, you should see a button that says e to the x. So I know on my calculator, if I can show you this, oops, it's right there. It's right above the ln button. Okay, it's like right above that ln function. So it's a second function on your calculators. So I want you to find that function, and you should be able to locate it on your calculators. If you can't locate it, you may have to contact me, and I might have to help you with it. But it should be there. Okay, if not, you're probably not using a scientific calculator. Now, if you can't find it, or if that button is for some reason is not on your calculator, E is the same thing as 2.72. So, I mean, instead of hitting the E to the X button, you could just use the number 2.72. So I guess you can just memorize that number if you want to. All right, but the base of the natural logarithm is the same thing as 2.72. So regardless, you can use either one. Okay. Anyway, so this might be a little bit confusing right here. So I think it's important just to kind of jump into a problem, and you'll see that this is actually pretty simple. So here it says consider a population of rabbits that has an initial population size of 10. So this is our n sub 0, right? This is our initial population. So it says, let's assume that the intrinsic rate of growth is 0.5 or 50%. All right, so they give you the intrinsic growth rate, so that's R. It says, which means that each rabbit produces a net increase of 0.5 rabbits each year. You might look at that and be like, well, how can 0.5 rabbits be produced? That number is just kind of an average. All right, so don't think that you can produce a half a rabbit, or a rabbit can produce half a rabbit. Anyway, it says, with this information, we can predict the size of the rabbit population 2 years from now. All right, so let's take a look at our equation again. So we want to figure out what the future population is going to be in 2 years, okay? So in order to find that, we have to understand all of these variables. So let's take a look here. Let's kind of just go step by step. So n sub 0 in this population is 10, right? There's 10 individuals. That's our initial population. So that number is going to be 10. Now we're going to multiply that number by e raised to the power of r times t. Now remember what e is, right? E is 2.72, okay? Or you can use that button on your calculator. But r, that's your intrinsic growth rate, which is 0.5. T is your time in years, which is 2. So, I mean, another way to write this, I guess if we're trying to simplify it a little bit, is just 10 times e raised to the power of 1, right? Because 0.5 times 2 is 1. So really, I mean, if you kind of just, again, simplify a little bit, if you want to plug in 2.72 for the e value, right? It's just 10 times 2.72 raised to the first power. Anything raised to the first power is just itself, right? So all we're doing here, really, if you punch it in your calculator, is 10 times 2.72, and we'll just round that number off to the nearest whole rabbit. So 27 rabbits. So what this is basically telling us is that if we have a population of 10 rabbits and it's growing at an intrinsic rate at 0.5, 2 years from now, we're going to have 27 rabbits. Okay. Hopefully that makes sense. So let's take it a step further here. Now we want to know how large the population is going to be after 4 years. Again, we're going to use the same equation, right? The initial population was 10. The growth rate is 0.5. But now we're trying to figure out what the population is going to be after 4 years. So all we're going to do is just take 10 times e raised to the second power, because 0.5 times 4 is 2, right? So you plug that into your calculator, 10 times 7.4, because e to the second power is 7.4, and then you end up getting 74 rabbits. So after 4 years, you get 74 rabbits. Now notice how the population, every 2 years, it's more than doubling. All right, this isn't just linear growth. This is actually exponential growth. Now let's do one more here. What if we want to know the population size 10 years from now? So same thing. Our initial population is 10. The population's growing at a rate of 0.5, but it's growing over 10 years. So 0.5 times 10 is 5. So all we're going to do is take 10 times the base of the natural logarithm raised to the power of 5, which is 148.4. Then you end up getting 1,484 rabbits. So I mean, imagine what this population is doing if it's growing intrinsically at this rate over time. Really, if you think about it, and if you were to graph this type of growth, this is what it would look like. This wouldn't be like linear growth. I'm going to show you another slide real quick. I'm going to come back to that. This is what we call exponential growth. This is how those rabbits are growing. This is showing us linear growth. This would be like if the rabbits were growing, let's say there was 10 rabbits, and then the next year there was 12, and then 14, and then 16. That would be linear growth. But this is exponential. We're more than doubling the population over time. All right, so I want you to notice one thing about this exponential growth curve. And this is kind of a generic curve, but we also call it a J-shaped curve because it has like this J shape to it. But there's kind of initially the growth is kind of slow, so you notice that the slope of this curve isn't really that high, but eventually the slope of it, gets very high. And that is showing us that the growth is increasing over time. The growth rate is. So, that is kind of a hallmark of exponential growth. I mean, think about zebra mussels, right? That's how they grow, right? They don't have anything limiting them, so they're going to grow exponentially over time. So, a few things here about exponential growth. Again, it's that J-shaped curve. Typically this type of growth we see when there's nothing limiting it. Again, when there's no limiting factors, that are kind of holding it down. Can populations grow like this forever? Realistically, probably not, right? But again, if there's nothing limiting them, then I suppose they can grow like this for a fairly long time. But eventually, something is probably going to limit that growth from continuing. All right, now this is what we call the logistic growth model. This is a little bit more realistic as far as what populations really do. Now you'll notice that this curve here, there's one kind of big difference between this curve and the exponential curve I showed you earlier. It's this dotted line. Okay, this dotted line represents something called the carrying capacity. And that number we talked about it the other day, that represents how many individuals that the population can support. If we're talking about fish in a pond or something, right, there's only so many fish that can be in that pond. If we're talking about, I don't know, zebra mussels in Lake Michigan, I mean, I guess Lake Michigan, there's only so many zebra mussels that Lake Michigan can support. It might be a pretty big number, but that number is there, right? That carrying capacity is in existence. So when you look at this curve here, it's kind of an S-shaped curve. You'll kind of notice that at the very beginning, right here, like this part of the curve, this is our J shape, right? We actually see exponential growth early on in the growth of this particular species or whatever this organism is. But eventually we get to a point, we call that the inflection point, where the growth starts to slow. For example, let's say we've got some zebra mussels and they're in Lake Michigan and they're starting to populate. So they're going to, grow probably pretty rapidly for a while, right? That's exponential. But eventually, if there are things limiting their growth, they're eventually going to slow down. Anytime growth gets past the inflection point, the growth starts to slow. And it gets slower and slower as it gets towards this carrying capacity. And eventually, if it kind of gets to a horizontal, that means that there's no growth. If the curve goes downward, if it slopes downward, there's actually negative growth. All right, so this inflection point is really important. Now, most of the time, invasive species are nowhere near their inflection point. Like invasives are they're like down here somewhere. They haven't quite hit that point yet. But most populations are probably have exceeded that inflection point and are probably nearing their carrying capacity. So there's also a way that we can kind of calculate that inflection point. If you know what the carrying capacity is, I mean, let's say, for example, there's, I don't know, a pond that can hold 1,000 fish. Well, if 1,000 is the carrying capacity, then the inflection point is half that. I mean, think about where this point is right here. If you kind of just went over on the y-axis, right, it's about halfway. So the inflection point is just k divided by 2. It's pretty simple to figure out what that number is going to be, at least hypothetically. All right, so again, logistic growth is sort of an S-shaped curve. And it's more indicative of what populations are really growing and how they're really growing, especially as they get closer to that carrying capacity. Now, last couple of things here, real quick. This is kind of a common thing that we see with a lot of populations, especially populations that grow fast. Like, let's say, for example, insects, like mosquitoes or something. Mosquito populations in the summertime, right? They just grow super fast, right? So you might get this exponential growth, this J growth, and you might actually get a population that overshoots its carrying capacity. So if it goes above that carrying capacity, you can probably imagine that it's going to come back down, right? Because that carrying capacity is how many individuals that the environment can support, right? So if we overshoot that, it's going to come back down. We call that a die off. And it might come back below the carrying capacity, then it might overshoot it again. It might come back down again. But you'll notice that, remember these oscillations, right? That's a term we talked about earlier in the year. These oscillations over time start to minimize. And eventually that population gets into what we call equilibrium. But it's not uncommon for populations to overshoot and die off several times before they eventually kind of balance themselves out a little bit. And here's an example here of an overshoot that actually happened with a species. Um, Earlier in the year, we talked a little bit about moose and wolves. I think I talked about them back um, just earlier in the year. I think I can't remember what topic it was we were talking about, but anyway, this was a place called St. Paul Island. It's up in Alaska, and it's a relatively small island. But back in the early 1900s, 25 moose were introduced onto the island. I can't remember how they got there. I think they got there by just walking across ice or something that had frozen, and they had gotten to this island. And then the ice melted. They were kind of stranded for a while, right? So what happened on this island was these moose had all the food that they needed. I mean, there was tons of vegetation, but there was also no predators. So there was nothing kind of keeping the moose, in check. So you would imagine if you've got a species like moose with unlimited food and no predators, then you can imagine what would happen to their population size. Right? I mean, we'll take a look at this like 25, 30-year span and just look at the shape of this curve, right? There was exponential growth. But you'll notice in like the late 1930s that the population started to come down. Well, what happened in the 1930s was the moose ate all of their food. There was nothing left for them to eat. So, without a way to get off of the island, literally the moose just starved to death and the population crashed. In fact, it crashed down to zero. There were no moose left on the island in 1950. So I want us to understand one thing about overshoots is if there is an overshoot, it will lead to a die-off, and that die-off could have drastic consequences because it could lead to extinction. Okay, so that's what's kind of an important lesson to learn from this particular example. All right, guys, that's it for me. Check out your buzz agendas for today. Make sure watch this again if you need to, or make sure you watch parts of it over again if you didn't quite understand it. All right, have a good day. Take care.